6, 7. Okay. Okay. It's too much. Too much retardation. Okay, let's just. Let's just do the most basic shit. Roadmap. Oh no, practice. And need code 150, please. I'm gonna cover some new topics just for the sake of it. I mean, I've did this before. It's a stack question. Ah, I don't like doing this. Nah. Bit manipulate. Okay, what should I do next? I need to do some different kind of problems. Not like a different kind of problems, but you know what I mean. Just like a let's do one, two, 250. Bro, I'm two brother, but I'm 250 though. You know what I mean? I'm 250 though. Stack, binary search, linked list, trees. Okay, let's do some more trees. But I need to. But I need to. I need to. I need your love. I need your love. Let's go, trees. How is it not working? Is it because this? I need your love. Ooh, ooh, Price. What even? Okay, let's do heaps. That's the order that he's prescribing us. But the industry was sleepy bitch. I'm walking. Know the devil. Maximum depth. So we need to find the depth of the binary tree. We can do an iterative method. I think that's the. How do I interpret this one? So one would be the root because I don't know, two and three, null and null, meaning null and null, four. I think the last null wasn't mentioned to be polite. So I need to find the depth, one, two, three, the depth of this thing. So one way I can do this is just to count how many times the iteration has gone on. So the count initially is going to be zero. Okay, the count initially is going to be zero. And we're going to call the max de, de, max de. We're going to call it. We're going to iterate over it. And we're going to call that, I think. We're going to increase the count every time it does its thing. And at the final iteration, we're just going to return the number. This thing, obviously. Okay, what? Recursive, that's what I mean. Okay. What the hell is going on? So this, yeah, return one plus max of self, you're gonna, what the fuck is going on? Iterative DSA stack? Not really, no. I don't really get it. Let's
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve maximum depth of a binary tree. And the main reason I'm solving this today is just for the sake of completion. We have solved harder tree problems before, but this one is on the blind 75 list, so I do want to solve this problem today. And this problem actually has multiple ways to solve it, so I do think it's a good problem to understand of like the fundamentals on tree traversals. We can do it 3 different ways, and I'm actually going to show the 3 different ways. There might even be more than 3, but I'm going to show you the 3 main ways. Basically, recursive depth first search, iterative depth first search, basically depth.
What the fuck is going, bro? Depth first search. What the fuck is this? What the fuck did you just write, bro? So yeah, recursive, iterative, and using a stack. Is that what it is? Yeah, I think this one uses a stack inherently, which is cool. Breadth for search, and that should be another depth for search. Cool. This is 104, so it's gonna be 104. And where is 104? 104. Oh no, don't do that. Don't do that, please. 104 is here. Bro, I had a brilliant idea. I just had a brilliant idea. Oh my god. I need to write it down. I need to write it down. Maybe not, maybe not. I don't want to write it down. It's not that brilliant now that I think about it. Okay, it's gonna be a fuck. What did I do? Okay, let's go back in. Uh, where is tree actually used? Uh, I don't need ChatGPT anymore. This is fucking retarded. I don't think it's been used anywhere. So let's just in computing DSA tree structure and algorithms, fundamental hierarchical data structure used to model data with parent-child response is everywhere in computing. Here's file system. Yeah, we know that. Networking, operating system, graphic. Maybe. No, no. In AI, how is it used? In AI, how is it used? Question mark, question mark. I think it's like one of those necessary things that we need to know. Let's just like go into it. Let's go.
First search without using recursion. And of course, another way is going to be breadth first search. So I'm going to be showing all 3 today. So the problem is pretty simple. We're given a root binary tree and we want to return its maximum depth. And the maximum depth is defined as being the longest path from the root to one of the one of the leaf nodes, and basically along that path we're counting the number of nodes. So in this case you can see we have 2 paths that are of the same length. So from the root down to here we have 3 nodes. From the root down to here we have 3 nodes as well. So those are the 2 leaf nodes we have here. We also have a leaf node on the left side, but clearly we see that there's only 2 nodes in this path. So out of all those paths, what's the max length? Of course, it's 3, so you can see that that's what our output is going to be in this problem. So the simplest way to solve this problem is recursive depth first search. Now, what's the base case? We're using recursion, so first let's think of the base case. Obviously, if we had just an empty tree, right? Like what if this was our tree? What are we going to return? Of course, 0, right? The max depth of an empty tree is just 0. What about if we just had 1 node and no children, right? Okay, we'd do this recursively, so we'd get to the first node, right, we'd say, okay, we at least have one node. Then we'd say, okay, let's just find the max of the left subtree and the max of the right subtree. Both of those are going to return 0, right? So once we get back to the root, what are we going to say? We're going to say, okay, the left and right subtree were 0, so the maximum of the left and right subtree is also 0. So what we're going to return from the perspective of this root node is just going to be 1 plus the max of the left and right results. Basically the max of the left and right subtrees, in which case it was both 0. So of course in this problem we're going to return 1 as the max depth. Now let's look at this more general example that they gave us. So obviously we're going to do the same thing. We're going to get to the root, say, okay, we found at least one node, so the depth is at least 1, and then we're going to return the max of the left and right subtrees plus 1. And why are we doing it this way? Well, you can see that we found this node, but now we have sub-problems, right? We need to know what's the max path, what's the max depth, and we'll have to search the left subtree and we'll have to search the right subtree. So we're not even considering this node anymore. We're doing recursion. We're looking at the sub-problem. What's the max depth of this left subtree? Well, of course, it's just a single node with no children, so of course the max depth is going to be 1. Similarly, let's do the right subtree, and so again, this is going to be our recursive case, right? We have one node, and from this node's perspective, we're going to run recursion again. We're going to look at the left subtree and the right subtree, both of which are going to return 1. So then, of course, from this node's perspective, we're going to return 2. The max depth of this subtree is 2. The max depth of the left subtree is 1. So now, when we get back up here, we're saying, okay, from the perspective of this node, we're going to return 1 plus the max of left and right. The max is clearly 2. So from this node's perspective, we're going to return 3. The max depth is 3. So let's code this up recursively. It's literally just going to be this line that I just wrote and the base case. And since we are traversing the entire tree, the time complexity is going to be big O of n. The memory complexity is just going to be the height of the tree, which also could be worst case big O of n if it's not a balanced binary tree. So with recursion, we always want to take care of the base case first. So if the root is null, then of course we're just going to return 0. That's the max depth. Otherwise, we're going to return 1 plus the max of what our DFS of left returns, or in this case, it's not DFS, it's actually called max depth. And since we're inside of the function, in Python, you have to, say self.maxDepth, and then run that on the left subtree, and also run it on the right subtree. Now, to make this line shorter, I could actually store the result of both of these function calls in variables, but I think this one-liner is pretty much good enough. So we're just taking the result of both of these function calls, figuring out what's the max of it. So what's the max subtree's depth of both of the...
Okay, I need to play around with crazy shit, man, crazy shit.
subtrees, and then just adding 1 to it, because we know that the current root node that we're traversing is definitely not null. So this calculation will work out. Let's submit it. And of course, I'm showing that I can't even solve easy problems, so it's not called node, it's actually called root. Hopefully you were able to...
Baby, we could chaka 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 chan chaka chan. What is going on? If it is not, if the tree is nowhere to be found. Okay, I understand that, but it's like, fuck me. This is magically gonna return. How? How? What is a nun type, bro? That's the first time I'm hearing it. Okay, let's do another one. Diameter, bro. No, how the fuck I'm supposed to find it? Okay, let's report what we just did. I think I did. We are self-calling it, and something happens. Lol. Diameter of the binary tree. I think this one is gonna be the diameter of the binary tree is defined as the length. The is defined as the length of the longest path between two tree. The path does not necessarily have to pass through the root. What? Return the. How do I do it? So the diameter is 2, 3. So 1, 2, 3. 3 long. Fuck you. Fuck you. Fuck, I just say, what the fuck is going on? How do I? So I think I need to call my. Okay, if not root, if it is not root, return null. Okay, and I need to return 1 plus that's the recursion. I don't think I need recursion for this one because recursion kind of means going top from bottom. It doesn't really talk about the width of how it is able to find it. Bro, why is the brute force this long? This shouldn't. Bro, what the hell? What the hell, bro? Why is this so difficult? Is this like a difficult one?
Hey everyone, welcome back and let's write some more neat code. So today let's solve diameter of a binary tree. We're given the root of a binary tree and we want to return the length of the diameter of the tree, which is defined as being the longest path from a particular node. So in this case, it would basically be the longest path on the left side, which could either be this part or this part. Both of those are of length 2. I'm getting that calculation because 2 is the number of edges on that side for the longest path. On the right side, we just have one edge, so that's 1. So the diameter through the root would be 2 plus 1, which is 3. But keep in mind that the longest path might not necessarily run through the root. So let's look at a counterexample. With this tree, if we try to calculate the diameter through the root, on the left side we have nothing, so that's a 0. On the right side we have 3. That's the longest path. You could take multiple different paths, but all of them are going to be of length 3, so the diameter from here is 3. But consider the node over here. Length on the left side is 2, and length on the right side is 2. So total is 4. That's the diameter of this tree. Now, I want to mention to you that this problem is actually closer to a medium problem than an easy problem. Why exactly is
Okay, let's not do it. Balanced binary tree. Given a binary tree, return true if the height is balanced and otherwise false. A height balanced binary tree is defined as a binary tree in which the left and right subtree of every node differ in height by more than 1. What? What the hell, bro? So I need to find if this by more than 1, it is more than 1. Return 0, and I need to find if um, self dot is balanced. Don't do that, please. Just give me this. Is balanced. What is root dot left? If the left is bigger, fuck me, kids. Ba 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 ba. More than or equal to 1. More than or equal to 1. I need to return uh, if it is equal to less than or equal to less than or equal to 1, I need to return true. Um, I think all of this should go here. No, 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 no. Go back. Um, return false. Bro, I'm such a genius. If this works. Wait, what? Wait, what? No, return false. You can return false. And this needs to return true. That is else if. Should I go else if? If it is zero, or I think I'm kind of getting closer to it. Maybe. Maybe I'm just like fucking around with test cases. I don't think this is. I think I need to let it like reiterate. And yeah, how do I? I think it should be like an else if, because I need to like go over everything, right? If it is, let's say, the height, and this is equals to each other. If both of them are equal to each other, then it is equal to each other, or okay, plus one, or I think it's one of them. This or yeah, let's try that. Bro, I'm such a genius. Oh my god. Oh my god, I'm such a genius. I don't think it's reiterating though. So I think this one is gonna be. Let's look at our test cases. Can you like show all the test cases it's wrong, maybe? Okay. I literally like fucking around with yeah. Bro, what the fuck is this, bro? Oh my god. Why is this so big? Can we just
Hey
Hello.
everyone, welcome back and let's write some more NeetCode today. So today let's solve the problem balanced binary tree. We're given a binary tree and we want to determine if it is height balanced. What exactly do they mean by height balanced? Well, it's defined by saying that for every single node in the tree, if we take the left and right subtrees of this node, the heights of these left and right subtrees will differ by at most 1. So in here you can see, taking a look at the root node, it has a left subtree. What's the height of this left subtree? Let's call it 1, right? Because there's one node in the left subtree. What about the right subtree? What's the height of this right subtree? Well, it's 2, right? We can determine that just by looking at it. So then the left subtree has a height of 1, the right subtree has a height of 2. The difference is at most 1, right? Because if we take the absolute value of the difference, we get 1. So we'll say the difference is 1. So we just did that for the root node, but we have to do that for every single node to make sure that the left and right subtrees of every single node differ by at most 1. And just to show you a counter example, so this is kind of a badly drawn tree, but take a look at the root node, right? If we take a look at the left tree over here, the height is 3. If we take a look at the right subtree, the height is 3. So the difference is 0, which fits into our criteria. So from the root node, the left subtree and the right subtree are balanced. But if we take a look at, let's say, this node, right, we take a look at its left subtree, which is empty, right? So that has a height of 0. The right subtree has a height of 2. So in that case, the difference is 2 minus 0, which is 2, right? Positive 2, which is greater than 1. So just because from here, taking a look at the root node, the left and right subtrees are balanced, doesn't mean that that's going to be true for every single node, because we just looked at this node, the left and right subtrees were not balanced. How can we solve this efficiently? Let me first show you kind of a naive approach, and then we'll see how we can actually optimize that. So if we were asking naively, right, the first question we're asking is, from the root node, are the left and right subtrees balanced? How do we even determine that? Well, do you agree that we could probably do a recursive DFS on the left subtree to determine the height of the left subtree, do a recursive DFS on the right subtree to determine the height of this subtree, and then we could compare those and make sure that the difference is less than or equal to 1. Do you agree that we could do that? Probably, right? I'll explain more details in the code, but for now, let's just assume we can do that.
I think I
We
did that.
start from the root, we run a DFS on the left and on the right. That means we go through
So,
every single node in the tree, so we just did an O of n operation, right? And we were able to determine, okay, from the root node, yes, it is balanced, but we're not done yet, right? Now we have to continue to ask that question for every single node, right? So the next question we're going to ask is, suppose on the left subtree, right? From the left subtree, are the left and right subtrees from this node also balanced? And of course, they're both 0, so we determine that they are. And then we'll have to recursively go to the right subtree. From here, we're going to ask, are the left and right subtrees balanced? Yes, they are, but we'll recursively have to continue. We'll have to do that from this node, and then we'll have to do that from this node. Since we're running a recursive DFS on every single subtree on this root tree, we're going to have to do basically an O of n operation each time we ask that question. Is it balanced from here? Is it balanced from here? Is it balanced from here? And we could have a really big tree, and we'd have to do an O of n operation each time. O of n is the number of nodes in the tree, and if we have to do this n operation n times, we're going to get a time complexity of O of n squared. So now the question is, can we do better than that? Is there any repeated work? And I'll show you that yes, there is repeated work, and it basically can be eliminated by asking the question in a different order. What I mean by that is, instead of first asking if the entire tree is balanced from the root node, right? That's the first question we ask. Is it balanced starting from here? Instead of asking that, we do this bottom up. We recursively, instead of asking it from here, we're going to check, okay, is this entire right subtree balanced? Before we do that, we're going to ask, is this entire subtree balanced? And we're going to keep going lower and lower until we get to the base case. Once we get to the base case, then we're going to go back up, bounced from this left and right child, left side, this subtree equal to 1. This node bounced. Before we return back up to the parent, we want to know what's the entire height of this.
look at the brute force sizes, man. The fuck? That's brute force, by the way. What the fuck is this even? Like, We are making another, the hell, iterative. Somehow the iterative seems the most logical. You're just having a stack, and yeah, the iterative seems pretty logical for some reason. I don't know if it's always like that, bro. I just the fuck.